We're now ready to talk about the theorem that has been one of our goals for the entire course, and that's the fundamental theorem of finite abelian groups. This is a classification theorem which tells us what all the possible groups are that are abelian of a given order, of a given finite order. This is a very important result that helps us to describe all groups with these properties. So we're going to start with just the statement of it, some applications, and then we'll go ahead and go into the proof. Now the proof does take some work, and we're going to rely on a lot of the results that we've had so far and put them together. In fact, the proof we're going to present in as a combination of various lemmas. So, Theorem 83, the fundamental theorem of finite abelian groups, says that if G is a finite abelian group, then there are two different representations that we can have. Then there exist prime numbers P1, P2, up through Pn, not necessarily distinct, and integers K1, K2, up through Kn, such that G is isomorphic to ZP1 to the K1 direct product with ZP2 to the K2 direct product up through ZPN to the Kn. For the purposes of this proof, we're going to use the notation ZL to mean the cyclic group of order L, so Z mod LZ. So any finite abelian group can be expressed as a direct product of cyclic groups where the order of the cyclic groups is a power of a prime number. Furthermore, this representation is unique. Up to rearrangement. Up to rearranging the orders of the factors in the direct product. So every finite abelian group can be represented uniquely this way, but there's another way that we can do it. So number two, there exist integers d1, d2, up through dm, such that for I equals 1 up through m minus 1, the number di divides di plus 1, and the group G is isomorphic to z d1, direct product z d2, direct product z d3, etc., up through z dm. And then this representation is unique. So this says that all finite abelian groups can be expressed as the direct products of cyclic groups, and furthermore, the orders of those cyclic groups are either all prime powers, or they can be set up in such a way so that the order of each group is a divisor of the next. So let's see how we can apply this. So let's find all abelian groups, that is up to isomorphism, of order 1, 1, 7, 6, where 1176 is 2 cubed times 3 times 7 squared. Now, usually the easiest way to classify the finite abelian groups of a given order is to use the first characterization of the theorem before. That is, we want to focus on the prime factors of the order of the group. And what we want to do is look at all of the different ways of grouping up the prime factors in the factorization of the order of the group. Or another way of saying that is all the different ways of expressing the order of the group as a product of prime powers. So one way that we have of doing that would be 2 cubed times 3 times 7 squared, the way that we had it before. So we could express 1176 as 8 times 3 times 49. That corresponds, under part 1 of the theorem before, to the direct product Z8, direct product Z3, direct product Z49. So this is one of the isomorphism. This is one of the isomorphism classes of finite abelian groups of order 1176. This is one of the possible groups that such a group might be isomorphic to. But then there are other ways of grouping up these prime factors. We could try splitting off one of the 2's and write this as 2 times 2 squared times 3 times 7 squared, which corresponds to writing 1176 as 2 times 4 times 3 times 49. So this is another factorization of 1176 into prime powers, but different because we've split up the 8 as 2 and 4. Now, this corresponds to the abelian group Z2, direct product Z4, direct product Z3, direct product Z49. And we can keep doing this. We can look at all the different ways that we can write 1176 as a product of prime powers. So we could have all of the 2's separate and write it as 2 times 2 times 2 times 3 times 49. And that gives us the group Z2, direct product Z2, direct product Z2, direct product Z3, direct product Z49. And then we have 3 more where we have the 3 different ways of expressing the 2's, and then but with the 7's split up. So we could take 2 cubed times 3 times 7 times 7, which is 8 times 3 times 7 times 7, which gives us the group Z8, direct product Z3, direct product Z7, direct product Z7, 2 times 2 squared times 3 times 7 times 7, which gives us 2 times 4 times 3 times 7 times 7, which corresponds to the group Z2, direct product Z4, direct product Z3, direct product Z7, direct product Z7, and then finally we could just have all of the factors split up, which corresponds to the group Z2, direct product Z2, direct product Z2, direct product Z3, direct product Z7, direct product Z7. So what we have here are 6 different groups of order 1176. All the different ways of taking direct products of cyclic groups with prime power orders in such a way that their product has the order that we care about. And the point of the fundamental theorem of finite abelian groups is that every finite abelian group of order 1176 is isomorphic to one of these six. Up to isomorphism, there are only 6 finite abelian groups of order 1176, and here they are. Now, we can see that they aren't isomorphic to each other because we had a theorem about when the direct product of two groups is a cyclic group. That happened when the two groups were cyclic and had relatively prime order. So for instance, comparing the first two groups in our list, we have Z8 in the first place, and then Z2 direct product Z4 in the second. Those two groups, ignoring the Z3 and the Z49 on the other side, are not isomorphic to one another because 2 and 4 are not relatively prime. So that shows that the two groups at the top are not isomorphic to each other, and the same thing holds true for the rest. All 6 of these groups are in fact distinct from one another. Now we can also take these descriptions in order to get a description in terms of the second way of writing down the groups in the fundamental theorem of finite abelian groups. Let's go ahead and take a look at the fifth one here. So 2, 4, 3, 7, and 7. Z2 direct product Z4, direct product Z3, direct product Z7, direct product Z7. In order to write this in the second form, what we want to do is we want to write this as a group of the form ZD1 direct product ZD2 direct product, etc., however many we need, such that D1 divides D2, which divides D3, etc., etc. So that's clearly not the case here. The way that we want to do that is we want to group up these groups by the prime number that their orders are a power of, and basically just arrange them in rows, with one row corresponding to each prime number that we've got. We could write this as Z2 direct sum Z4, and then we've got Z3, and then we have Z7 direct product Z7, and so we know that the group that we're looking at is the direct product of all these groups, and what we want to do is we want to just group them up by arranging them in rows according to their to the prime number that they're based on, and in increasing order as we move from left to right. What we can do is just take the direct product of all the terms in each column to get a new description. So we know that Z2, the direct product of Z2 and Z7, is isomorphic to Z14 because 2 and 7 are relatively prime. Also, 4, 3, and 7 are all relatively prime, and therefore the direct product of Z4, Z3, and Z7 is the cyclic group with order 4 times 3 times 7, which is 84. And so another way of writing down this same group would be as Z14 direct product Z84. And here we have that 14 does divide 84, and so that would be another way of writing down this group. And you could do the same thing with all of the groups in our list here. in order to get those descriptions of it. In fact, when you do that, you will find that the first group in our list, in fact, let me move things a little bit here. You'll find that the first in our list is actually just the cyclic group of order 1176. We know that had to show up somewhere in there, and that's what that one is. Let's see, the one that we did just now, we saw that that's Z14, direct product Z84, and we can similarly work with the rest of these. This is Z2, direct product with, Z588. Yes. The third one is the direct product Z2, Z2, Z294. Next one would be Z7, direct product Z168. And let's see, the last one works out to be Z2, direct product Z14, direct product Z42. So we have these two different ways of describing finite abelian groups, and we have uniqueness statements for them, which is nice. It means that given any finite abelian group, we know that we can always find some group written in these ways for us to that it is isomorphic to. So so let's see an example of this. Which group in the previous descriptions, or in the form of the previous descriptions, is Z mod, let's see, which one do we go? Z mod 15Z cross isomorphic to. This is going to be a finite group. It's going to be a finite abelian group because the multiplication in this group is commutative. We know that the elements of this group are of the form 1 bar, 2 bar, 4 bar, 7 bar, 8 bar, 11 bar, 13 bar, and 14 bar. Those are the representatives of the numbers that are relatively prime to 15, and we can see that there are 8 of them. So the order of Z mod 15Z cross is 8. So that means that Z mod 15Z is isomorphic to one of the following. We have that 8 is equal to 2 cubed. So there are 3 ways that we can write it down. We can write it as 2 cubed. We can write it as 2 times 2 squared. Or we can write it as 2 times 2 times 2. There are only 3 finite abelian groups of order 8. So this group Z mod 15Z cross is isomorphic to either Z8, Z2 direct product Z4, or Z2 direct product Z2 direct product Z2. One of the best ways of determining which one it is to identify the order. So let's look at the orders of each of the elements inside this group. We have that the order of 1 is 1. Turns out that the order of 2 is 4, 2 bar is 4, the order of 4 bar is 2, the order of 7 bar is 4, the order of 8 bar is 4, the order of 11 bar is 2, the order of 13 bar is 4, and the order of 14 bar is 2. So we can look at these orders and we can note that there is no element in here that has order 8. So no element of order 8 means that this group is not isomorphic to Z8. This is not a cyclic group. But we note that it has elements of order 4, which means that it's not Z2 direct product Z2 direct product Z2. Remember that in a direct product of cyclic groups, the order of an element is the least common multiple of the orders of all of their components. Or not just in direct product of cyclic groups, but in a direct product of all groups. And so if we look at the group Z2 direct product Z2 direct product Z2, the only orders possible in each of these groups, in each of the groups Z2, are 1 and 2. And now if we take the least common multiple of orders, where the orders come from 1 or 2, we're only ever going to get 2 or 1. So all elements of Z2 direct product Z2 direct product Z2 have order 2 or 1. In particular, none of them have order 4. So that means that our group is not isomorphic to Z2 direct product Z2 direct product Z2. And so, since the only one left is Z2 direct product Z4, and the fundamental theorem of finite abelian groups says that Z mod 15Z cross has to be isomorphic to one of them, we have that Z mod 15Z cross is isomorphic to Z2 direct product Z4. Now, this is our first example of what could be considered a non-constructive isomorphism, because we have that these two groups are isomorphic, but the work that we've done so far doesn't show what the isomorphism is. We haven't exhibited a function that goes between them, a bijective homomorphism. Now, we're guaranteed that such a bijective homomorphism exists by the theorem, but it's not clear from, or we don't see that just from the argument that we've done. All right, so that's the fundamental theorem of finite abelian groups, how we use it. Let's get into the proof, and this is going to have several pieces to it. So let's strap in and get started. So proof of theorem 83. Now there is one component to the argument that we're going to be doing that relies upon a theorem that we're not going to be proving. It's completely correct, but the proof of it is technical enough that we're not going to spend time on it here. The main place it shows up is when we prove uniqueness, which isn't going to be till the end, but it does have some interest in its own right. So we're going to go ahead and put it here, theorem 84. Let G, H, and K be groups with G a finite group if the direct product of G and H is isomorphic to the direct product of G and K, then H is isomorphic to K. So this is saying that we have a sort of cancellation of groups with the operation of direct product. However, do be aware that this does rely on the order of G being finite. This theorem doesn't necessarily hold if we're looking at infinite groups. However, all the groups we're going to care about in this problem are, of course, finite, and so Theorem 84 will apply just fine. All right, so the way that we're going to prove the Theorem 83, the fundamental theorem of finite abelian groups, is going to involve constructing quite a few internal direct products. And so remember that if G is a group, H and K are normal subgroups of G, such that their intersection is just the identity, and their product is the whole group G, meaning that every element of G can be expressed as a product of H and K, then G is isomorphic to H direct product K. We are going to be using this quite often. And recall, this is what we call the internal direct product. In fact, the first step in our process is proving that we can always construct such an internal direct product when we're working with a finite abelian group. So let's look at lemma A. We're going to wind up having 4 lemmas here, lemma A, B, C, and D, that we're going to combine together in order to make the proof of Theorem 83. So lemma A says let G be a finite abelian group of order P to the n times m, where P does not divide m. So we've got the order G. We got the order of G can be expressed as P, power of P times m, where P doesn't divide m, so we've listed out all the powers of P we can get, and P is a prime number. Then let's let H be the set of all elements of G such that x to the P to the n equals the identity. So this is all elements of G where the order of x is a power of P. And let's let K be the set of all elements x in G such that x to the m is equal to the identity. So this is the set of all elements of x, or elements of G, where the order of x divides m. Now, because P doesn't divide m, it's going to turn out that there's going to be no overlap between these two. In fact, that's part of the conclusion. We have that G is isomorphic to H direct product K, and furthermore, we have that the order of H is exactly P to the n. So we're going to prove the isomorphism statement of the theorem by showing that that G is an internal direct product of H and K, and then we're going to make an argument based on Lagrange's theorem in order to get that the order of H is exactly P to the n. So, first of all, since G is abelian, then all subgroups of G are normal, therefore H and K are subgroups of G. Incidentally, we technically didn't show that H and K are subgroups. It's not hard to see that they are, and since they are subgroups, they are abelian. They are normal subgroups because G is abelian. So now let's suppose that X belonged to H and K at the same time. Then that means that X to the P to the N equals the identity, and X to the M equals the identity. So, in particular, that means that the order of X divides both P to the N and M. But since P to the N and M are relatively prime, this is because P itself is a prime number, and therefore, if it doesn't divide M, then it's relatively prime to M. So since P to the N and M are relatively prime, this means that the order of X has to equal 1. That's the only number that divides both P to the N and M. So that means that X has to be the identity. That's the only element with order 1. So that tells us that H intersect K is just the identity. So we are almost there. We've shown that H and K are normal subgroups of G. We've shown that their intersection is trivial, and so it remains to show that every element of G can be expressed as a product of an element of H and an element of K. Let's get a new page for this. So now let's let X be any element of G. Now since P to the N and M are relatively prime, there exist integers S and T such that 1 equals Sm plus T P to the N. We can always express the greatest common divisor of two numbers as a linear combination this way with integer coefficients. So that means that X is equal to X to the first, which is the same as X to the Sm plus Tp to the N, which is X to the Sm times X T P to the N. Okay, so what we've done is we've taken any element of G and we've expressed it as a product of two things here. What we're going to claim is that this first term here belongs to H, and this second term here belongs to K, which will show that X belongs to the product HK, which will finish up what we want to do. Now, to show that X is an element of H, we need to show that to show that X to the Sm is an element of H, we need to show that when you raise it to the P to the nth power, you get the identity. If we take S to the Sm to the P to the nth power, that's the same as X to the MP to the N to the S power. But M times P to the N is the order of G. And if you take any element and raise it to the order of the group, you get the identity. So that tells us that X to the Sm belongs to H. So we can do a similar thing here. If we want to show that X to the Tp to the N belongs to K, then we need to show that when we raise it to the mth power, that we get the identity. And this is going to go pretty much the same way. If we have x to the t p to the n raised to the m, that's the same as x to the m p to the n raised to the t. Again, m times p to the n is the order of g, and therefore we get the identity to the tth power, which is just the identity. So that tells us that x to the t p to the n belongs to k. So hence, x itself belongs to the product, the set hk, and so this means that g equals hk because x was completely arbitrary in this process. So since h and k are normal subgroups of g, h intersect k, pardon me, is the identity, and g is equal to hk, we have that g is isomorphic to the direct product of h and k by Theorem 81. All right, so that handles the first part of lemma A, that we can always find these H and K subgroups that that contain elements that go to the identity when you raise to the p to the nth power, and those that do when you raise to the mth power. The next thing that we want to show is that the order of H is exactly p to the n. All right, so by Lagrange's theorem, we have that the order of hk is equal to the order of h times the order of k divided by the order of h intersect k. But we know that the order of hk is the order of g, because we just showed that g is equal to h times k, which is p to the n times m. And the order of h intersect k is equal to the order of the singleton set containing the identity, which is just 1. So that tells us that p to the n times m is equal to the order of h times the order of k. Now, by Theorem 68, since H only contains elements with order of power of P, the order of H must be a power of P. Also, since K contains no elements of order P, the order of K is not divisible by P. So when we look at the equation p to the n times m equals the order of h times the order of k, and we know the order of h has to be a power of p, and we know that the order of k can't contain any factors of p, then the only way for that to happen is for the order of h to be the p to the n, and for the order of k to be exactly m. And so that finishes off lemma A. So what this means, if we apply lemma A repeatedly, is we can do the following. Given any group G and prime number P, we can let G subscript P be the set of all elements X in G, so that the order of X is a power of P. And what lemma A says is that if I have an abelian, a finite abelian group G, then for any prime number P, G is isomorphic to GP, direct product some other subgroup H, where H has no elements with order a power of P. But then we can repeat this process and choose a different prime number. So now let Q be another prime number. We can write H as GQ, direct product K, where GQ is the set of all elements of G, where the order of X is a power of Q, and K has no elements of order P or Q. So we could in fact write G as GP direct product GQ direct product K. And every time we do this, we are taking particular subgroups of G, the set of all elements with order a power of P, then the set of all elements of order power of Q, and then another prime, and then another prime, and then another prime. And so in particular, if P1, P2, up through Pn are the prime divisors of G, then in fact G is isomorphic to GP1, direct product GP2, direct product GP3, and in fact once we get to the last one, GPN, we stop, because if we had another subgroup off to the side here, J here, it would have to include all the elements with with order not divisible by P1, P2, P3, etc., up to Pn. But the only element that does that is the identity, and taking the direct product with the identity is just isomorphic to not taking the direct product at all. And I should specify here up here where I said H has no elements with order a power of P. That's not incorrect, but we need to be more precise. So this is H has no elements with order divisible by P. And down here with K has no elements with order divisible by P or Q. So this is a good first step in our decomposition. It shows us that we can take a group G and decompose it into a direct product of groups that look sort of like what we're looking for. a direct product of groups where every element in that group is a power of some prime number. However, these groups GP1, GP2, etc. will usually not be cyclic groups. And so lemma B, our next lemma, tells us how we can take a group that looks like this GP1, GP2, GP3 and decompose it further using cyclic groups. So let's look at lemma B. Lemma B says, let G be a finite abelian group with the order of G a power of a prime number P. Furthermore, let A, B, and G be of maximal order. You look at all the elements of G, and whatever the maximum order that anything has in that group, choose one element that has that maximal order. There exists a subgroup K of G. It will be normal, but there exists a subgroup K of G such that G is isomorphic to the cyclic subgroup generated by A and K. Now, this lemma we are going to prove again by showing that the cyclic subgroup generated by A and K give us an internal direct product, that G is the internal direct product of these two subgroups. So let's prove this one. We're going to do this by induction on the number n. So we use induction on n. Oh, pardon me, I did leave something out of the statement here. Rather than just stating the conclusion of saying that these two are isomorphic, we actually do want to know that there exists a subgroup K of G such that the cyclic subgroup generated by A intersect K is just the identity, and that G is the product of the cyclic subgroup generated by A and K. Or yeah. So in particular, this means that G is isomorphic to the direct product of those two. The reason why we need to specify these is that in our later lemmas, or lemma C, we're actually going to use explicitly the fact that we have these properties. All right, so the proof. We use induction on n. Now the base case is if n is equal to 1. If n is equal to 1, then the order of G is P, and so we have shown before that G is itself cyclic. So we may let A be any non-identity element of the element of G, and let K just be the trivial subgroup containing only the identity. So that means that the cyclic subgroup generated by A intersect K is just in fact equal to K, which is the identity, and G is the cyclic subgroup generated by A times the identity, which is just the cyclic subgroup generated by A, but that's going to be G because A is a generator of G. So in the base case, if n equals 1, then we have the result. Let's let n be greater than 1 and assume the result is true for any group G prime with the order of G prime equals p to the k, where k is less than n. So we're using strong induction here. All right, so in this case, we'll now let A, B, and G be of maximal order. And we'll let the order of A be written as p to the m. Because the order of G is a power of p, then the order of any element of it has to be a power of p. Now, if m is equal to n, then that means that G is actually a cyclic subgroup generated by A, and again, taking K to be the trivial subgroup generated by E, we're done. Exactly as in the base case. So let's assume that m is less than n. So the situation we're in here, we've got the group G. It has an order which is a power of p, and we've chosen an element A of the group that has maximal order, but that order isn't the same as the order of the group. So the group G is not cyclic, but we've got some element A here that has the greatest order out of anything we could find in there. Now, since the order of A is maximal in G, we have that for any element x in G, we have that x to the p to the m is the identity. If that wasn't the case, then x would have an order greater than the order of A, which violates the maximality of the order of A. All right, so we've got our setup here. I'm just going to put up here to remind us, we have that the order of G is p to the n, the order of A is p to the m, and for all x in G, we have that x to the p to the m is the identity. All right, so now let's choose B in the group, but outside the cyclic subgroup generated by A, because we've assumed that that we can do that, with minimal order. We look at all of the elements of the group that aren't in the cyclic subgroup generated by A, look at all of their orders, and choose an element with minimal order. We claim that the cyclic subgroup generated by B and the cyclic subgroup generated by A only intersect in the identity. So let's see why that would have to be. Since the order of the element B to the P has to be less than the order of the element B, in fact, it has to be the order of B divided by P, we must have that B to the P belongs in the cyclic subgroup generated by A, because anything with order less than the order of B has to be in this subgroup generated by A. So that means that we can let B to the P be A to the I for some I. There always exists an I that does that. So now, remember that we have that if we take any element and raise it to the P to the mth power, then we get the identity. So in particular, B to the P to the m is the identity, but that can be split up. That's the same as B to the P times P raised to the P to the m minus first power. We've assumed that B to the P is equal to A to the I, and therefore that means that A to the I, P to the m minus 1 is equal to the identity. So that means that the order of A to the I is less than or equal to P to the m minus 1. So in particular, this means that the cyclic that A to the I is not a generator of the cyclic subgroup generated by A, because the cyclic subgroup generated by A has order P to the m, and the order of A to the I is less than that. And so another way of saying this is that the greatest common divisor of I and P to the m is greater than 1. Back when we were talking about cyclic groups, we had all these equivalent conditions for when an element of a cyclic group is a generator for that cyclic group, and the element A to the I would be a generator if and only if the greatest common divisor of I with the order of the cyclic group was 1. Since A to the I is not a generator of the cyclic subgroup generated by A, it's the greatest common divisor of I and P to the m is greater than 1. So that means that there's some number that divides both P to the m and I, which is greater than 1. But the only numbers that divide P to the m are powers of P. So that means that hence P has to divide I. So let's say that I is equal to P times J. The I that we found here has to be a multiple of P. So then we have that B to the P is equal to A to the I, which is equal to A to the Pj. Now, let's consider the element C. This element C is going to be A to the negative j times B. Now, if C were in the subgroup generated by A, then so would B. B in the cyclic subgroup generated by A contradiction. So C is not in the cyclic subgroup generated by A. This, by the way, is the case since if C were in the cyclic subgroup generated by A, then that means that A raised to some number L would be equal to A to the negative JB. And if we multiplied both sides by J, then we get A to the L plus J is equal to B, which means B would be in the cyclic subgroup generated by A, which we know is not the case. So that tells us that C is not in the cyclic subgroup generated by A, but also we have that C to the P is equal to A to the negative JB to the P. Because our group G is abelian, we can distribute this through to get A to the negative JP B to the P, which is a to the negative I, b to the p, but a to the I was b to the p. So this is b to the negative p times b to the p, which is the identity. So this shows that C is not in the cyclic subgroup generated by A, and the order of C is equal to P. Now, since B was or has the minimal order of elements outside A, outside the cyclic subgroup generated by A, we must have that the order of B has to be equal to P also. So, or let me be slightly more precise. We must have that the order of B has to be less than or equal to the order of C, which is equal to P. But the order of B is not equal to 1 because B is not the identity, and it also has to be divisible by P, and so that means that the order of B has to in fact be equal to P. Now this is actually really important. What this means is that hence any non-identity element of the cyclic subgroup generated by B generates the cyclic subgroup generated by B because it's the cyclic subgroup with order P, a prime number. So if the cyclic subgroup generated by A and intersect the cyclic subgroup generated by B contained a non-identity element X, then we would have that the cyclic subgroup generated by B is equal to the cyclic subgroup generated by X, and then in this scenario, X would be an element of the cyclic subgroup generated by A, and therefore that would mean that the cyclic subgroup generated by X is a subgroup of the cyclic subgroup generated by a contradiction. A contradiction since we know that B is not in the cyclic subgroup generated by A. So that was a lot of work proving the following. Hence, the cyclic subgroup generated by A intersect the cyclic subgroup generated by B is, in fact, simply the set containing the identity element. Now, unfortunately, it's not the case that the group G that we're starting with is going to be the internal direct product of the subgroup generated by A and the subgroup generated by B. They have the intersection property that we want, but it's probably not the case that every element of G can be written as a product of something in the first group and subgroup and something in the first subgroup. We're going to have to work a little bit harder to find this subgroup K that's going to do what we want. However, we're going to do that by using induction, by quotienting by the cyclic subgroup generated by B. So now, let's let G prime be the group G mod the cyclic subgroup generated by B. And then for the sake of notation, for an element X coming from G, let's let X bar be the coset of the cyclic subgroup generated by B in G prime with representative X. That's just going to make our notation much easier. Now, we want to identify a few things about what happens to our various elements as we move from G down to G prime. Now, if the order of A prime were less than the order of A, we know that the order of A prime can't be any bigger than the order of A, but it might be less than it in general. But if the order of A prime were less than A, then that would mean that A prime to the P to the M minus 1, so that's the next smaller possible order you could have. That would tell us that this is equal to E bar, which is the coset, which is just the subgroup generated by B. Hence, this would tell us that A to the P to the M minus 1 is in the cyclic subgroup generated by B, which is a contradiction to the above, because we know that a contradiction, since A to the P to the M minus 1 is not the identity. And we've already shown that the only things that are in common between the subgroup generated by A and the subgroup generated by B is the identity element. So this shows that the order of A bar is in fact P to the M, which is the order of A. So, in particular, this means that A bar is an element of maximal order in G prime. Everything in G prime comes from G. Everything in G prime is of the form some x times the subgroup generated by B. And in fact, back when we looked at factor groups, we saw, or really rather this was when we were talking about homomorphisms, we saw that the order of an element when you move from a group down to a factor group can't get any bigger. And so the only thing that might happen to the orders of elements as you move from G to G prime is that they get smaller or they stay the same. Now we've shown that the order of A bar is the same as the order of A, and the order of A was already the biggest order that appeared anywhere in G, and therefore it's at least as big as the order of anything in G prime. And so, since the order of A bar is equal to the order of A, it has to have an order greater than or equal to everything else in G prime. So now here's where we finally use our induction step. We have assumed that the statement of the theorem that we started with holds whenever we're looking at a group with order less than P to the N, or with order P to the K for some K less than N. So since the order of G prime is equal to, well, it's the order of G divided by the order of B, which is certainly less than the order of G. By induction, there exists a subgroup K prime of K prime of G prime, such that the cyclic subgroup generated by A prime, A bar, this now lives inside G prime, intersect K prime is equal to the identity element in G prime, and such that the cyclic subgroup generated by A prime times this subgroup K prime is equal to G prime. So now let's let K be all of the elements in G such that X bar belongs to K prime. This can also be thought of as the inverse image or the pre-image of K prime under pi, where pi going from G to G mod the cyclic subgroup generated by B is the projection map. All right, now we are going to claim that this K that we've constructed satisfies the conditions that we need for this lemma. That that the intersection of this K with the cyclic subgroup generated by A is just the identity element, and that if you take the cyclic subgroup generated by A and multiply it by this subgroup K, you get the whole group. And we're going to base that on the facts that we have similar statements happening on the level of G prime. So let's make that explicit. We claim that the cyclic subgroup generated by A intersect K is just the identity, and the cyclic subgroup generated by A times K is all of G. If X belongs to the cyclic subgroup generated by A intersect K, then that means that X bar will belong to the cyclic subgroup generated by A bar intersect K prime, which by our construction is just the identity element inside G prime. So that means that X bar is equal to E bar, which is the cyclic subgroup generated by B, and so that means that X itself belongs to the cyclic subgroup generated by B. So since X also belongs to the cyclic subgroup generated by A, that's what we assumed about X, we have that X is in the cyclic subgroup generated by A and the cyclic subgroup generated by B, but we've already shown that this intersection is just the identity element. So hence, X is the identity element, and so that tells us that the subgroup generated by A intersect K is just the identity element. All right, nearly there. Nearly there. It just remains to show that every element of G can be written as some element of the cyclic subgroup generated by A and some element of K. So now, let's let X be some element of G. We're going to try to show that X can be written in the form something in the cyclic subgroup generated by A times something in K. And we're going to do that again by dropping down to the level of G prime, where we know that the similar statement holds for the subgroup generated by A bar and the subgroup K prime. So since we have that G prime is equal to the cyclic subgroup generated by A bar and K prime, we have that X bar is equal to some power of A bar times Y bar for some Y bar in K bar. So therefore, if we get rid of the bars, then what that means is that X times the cyclic subgroup generated by B is equal to a to the I y times the cyclic subgroup generated by B. And so this means that x inverse times a to the I y belongs to the cyclic subgroup generated by B. We're just using the facts of what it means for two cosets of a subgroup to be equal. So therefore, x to the -1 a to the I y is equal to b to the j for some j. Rearranging, we have that x is equal to a to the I y b to the -j. Now, we're almost there. We know that a to the I belongs to the cyclic subgroup generated by A. That's fine. So all we have to do next is to show that y times b to the -j belongs to k. Now remember that k is defined by being those elements that are representatives of elements of k prime. So now, if we have y b to the -j bar, that is by standard operations on factor groups, this is y bar times b to the -j bar. But that's y times the cyclic subgroup generated by B times b to the -j times the cyclic subgroup generated by B. And remember that when you take the coset, or you take a representative from a coset that actually belongs to that coset, you get just the same coset back. So b to the -j times the subgroup generated by B is just the subgroup generated by B again. And remember that the subgroup generated by B is the identity element inside the group G prime. So that tells us that y b to the -j bar is equal to y bar, and y bar was in k prime. Thus, that tells us that y b to the -j belongs to k, and so x belongs to the cyclic subgroup generated by A times K. And finally, we are done with lemma B. So by induction, the statement holds for all n. Let me go ahead and make this second last sentence much more precise. Therefore, our last argument here showed that G is equal to the product of the cyclic subgroup generated by A and this subgroup K. And by induction, this holds for all n. So now lemma B is proved. Lemma B is definitely the most intense lemma that we're going to have to prove here. Lemma C is really just taking lemma B and applying it repeatedly, and then lemma D is just going to handle the uniqueness portion of it, which isn't too bad. All right, so let me actually review what we have so far. So lemma A essentially says that we can write any group as a direct product of GP1, GP2, up through GPN, GP subscript n, where the GPIs are the set of all x's in G, such that the order of x is a power of pi, where these pi's are prime. Lemma B says that essentially, breaking it down to what we really care about, it says that if the order of G is equal to p to the n for some n, then there exists an element A in G such that G is a direct product of the cyclic subgroup generated by A and K. I should say there exists an A in G and a K subgroup of G such that G is a direct product of the cyclic subgroup generated by A and K. So lemma C is going to take lemma B and say, basically, we can do this repeatedly and write down any G whose order is the power of a prime as a direct product of cyclic groups. All right, so let G be a finite abelian group with the order of G p to the n for some prime number p. There exist cyclic groups G1, G2, up through Gm. And these are all, in fact, subgroups of G, such that G is isomorphic to G1, direct product to G2, up through the direct product of Gm. So this says that any finite abelian group of prime power order can be written in as a product of cyclic groups. So the proof of this is by induction. We use induction on n. If the order of G is just equal to p, that is, if n is equal to 1, then G is itself cyclic. So we're done. Let's suppose n is greater than 1, and the result is known for all k less than n. So now let A, B, and G be an element of maximal order, p to the m. If m equals n, then G is cyclic, and we're done. If not, then by lemma B, G is isomorphic to the cyclic subgroup generated by A and K for some K a subgroup of G. Now we have that the order of K is equal to the order of G divided by the order of the cyclic subgroup generated by A, Lagrange's theorem. And that tells us that the order of K is equal to P to the N divided by P to the M is P to the N minus M, and in particular, this is less than P to the N. So this tells us that by induction, K is a product of cyclic subgroups. And that does it, because that shows that G is isomorphic to a product of the cyclic subgroup generated by A and K. By induction, K is going to have smaller order than G, and by induction, it can be written as a product of cyclic subgroups of K, but subgroups of K are also subgroups of G to begin with, and so by induction, we get that K is a product of cyclic subgroups, and therefore G is a product of cyclic subgroups. So this, putting lemma A, B, and C together gives us most of what we want. So lemma A, B, and C together give us that given any finite abelian group G, we can write G as a product of GP1, GP2, GP3, up through GPN. And each GPI can be written as a product of cyclic groups of the form Z Pi to the Ki j. We know that every cyclic group is isomorphic to one of these Z groups, and so that means that each GPI can be written as ZPI to the Ki1, direct product ZPI to the Ki2, direct product up through ZPI to the Ki mi. So G can be broken up into the groups GPIs. The GPIs can be broken up into these ZPIs, and so this shows that G can be written as a direct product of cyclic groups of prime power orders. So G is isomorphic to ZP1, K1, ZP2, K2, up through ZP L, K, L, where now these P1s through PLs are not necessarily distinct as they were with the GP1 PIs. So that gives us essentially the existence part of the fundamental theorem of finite abelian groups. The last thing to do is to prove the uniqueness, that if I have if I describe G in this way, then it's essentially unique. That is where the only difference could be in the rearranging of the pieces. So to handle uniqueness, first of all, notice that the groups GPI are uniquely determined, because each one of these GPIs is simply the set of all elements whose order is a power of the prime number pi. There's no wiggle room there. There's no ambiguity. It just is what it is. Where there is some potential ambiguity is in our lemmas B and C. There were choices to be made. So in lemma B, we said, choose an element of maximal order. There could be lots of elements of maximal order. Does it make a difference? Also in lemma B, we chose this K subgroup. Is that K subgroup unique? And the answer is no. It's not necessarily unique, and it depends on your element of A that you choose. So there's lots of potential non-uniqueness in the construction that we did in lemmas B and C, but not for lemma A. And so really we only need to make sure that the decompositions of the GPIs are unique. And that's what lemma D is going to prove. So lemma D says, let G be a finite abelian group of order p to the n, where p is a prime number. And then suppose that G is written in a couple of different ways. That we have ZP to the I1 direct product, ZP to the I2 direct product, up through ZP to the IR is one way of writing G down as a product of cyclic groups. But let's say that we have also written it as ZP to the J1 direct product, ZP to the J2 direct product, up through ZP to the JS. And let's make sure that we fix the orderings. Let's fix it so that I1 is less than or equal to I2 up through IR, and J1 is less than or equal to J2 up through JS. In this case, R in fact has to be equal to S, and each IK equals the JK for all K. All right, so this is saying that if we specify that we're going to be writing down our decomposition in ascending order of the cyclic groups, then in fact there's no difference. There's only one way of doing this. All right, so let's do the proof. Let's use induction again on n. If G or if n equals 1, then G is cyclic. So in that case, we must simply have that G is isomorphic to ZP to the P to the I1, which is isomorphic to ZP to the J1. There must be only one term on each side of the decomposition, and so that must mean that I1 has to be equal to J1, because it's not possible for two cyclic groups of different orders to be isomorphic. So now let's suppose that n is greater than 1 and the result is known for groups of order less than n. Let's let A be in G be an element of maximal order. As we've done before, of maximal order, and we'll call it P to the M, just as we have been doing. By lemma B, G is isomorphic to K direct sum, the cyclic subgroup generated by A, for some subgroup K, hence G is isomorphic to K direct sum Z P to the M. We have this. Now, let me copy this decomposition onto the next page. Now we have that the maximal order of an element of G is P to the M. Now, since the maximal order of an element of the left-hand side of the isomorphism above is P to the I R, we must have that P to the I R equals P to the M, so that means that I R is equal to M. So that means that we have that Z to the Pi1 direct product up through ZPI R minus 1 direct product ZP to the M. Let me move this around. Is isomorphic to G, which is isomorphic to K direct product ZPM. This is what we had when we worked out that on the previous slide. So now notice that we have on the left-hand side of this isomorphism a group with a direct product Z to the PM, and that's isomorphic to the group K direct product with the subgroup with the group Z to the PM. So now, by Theorem 84, which says that when one of our subgroups is finite, we can cancel those subgroups. So by Theorem 84, ZP to the I1 direct product up through ZP to the I R minus 1 is isomorphic to K. Now we can run through the exact same argument on the other side with the P to the J's. Similarly, we have that ZP to the J1 direct product up through ZP to the IS minus 1 is isomorphic to K, and we have that, JS minus 1. And we have that JS is equal to M. Well, now we can use induction because now we've got K decomposed two different ways as a product of cyclic groups. Since the order of K is equal to the order of G divided by P to the M, which is certainly less than the order of G, by induction, we have that R minus 1 equals S minus 1, and IK equals JK for K between 1 and R minus 1. But we already determined that IR equals JR because they both equals JS since they both equal M. So that means that R equals S and IK equals JK for all K's between 1 and R. And that finishes off the uniqueness portion of the fundamental theorem of finite abelian groups. This is certainly the most complex theorem that we've proved. It's used a whole lot of the results that we built up throughout the semester. We worked with direct products, obviously a huge amount, but we also dealt with factor groups a lot. We used induction. We used lots of properties of cyclic groups as we're working through this, properties of abelian groups and so forth. So this result is really the culmination of a large amount of work that we've done. And now we totally understand, or we can at least classify abelian groups. Every abelian group is a product of cyclic groups, and in particular, they're products of cyclic groups of prime power orders, or of cyclic groups whose orders are arranged in this divisibility pattern. So this is one of the best theorems, one of the shining lights in the first in one's first encounter with abstract algebra, and it's just it's really amazing the way everything comes together.